And we are live.
Hello, everyone. Thank you very much for joining us this morning for our live session. This is Matthew. I'm going to hand the session over to Chris, and we will start with your questions. We'll grab some from email, and then we will also grab some from the live chat. So make sure you ask them in there. Thanks for joining us.
Okay, welcome everyone to another live session in the online course. Once again, coming to you from London, where it's late afternoon, where it's April, where it's still very cold, about 38 degrees, where Brexit is looming now a week from now. It's supposed to have happened last week, but didn't. Now it's going to happen in a week or so. Very exciting over here. Ready for your questions on astronomy. Don't ask me about Brexit. I have nothing to say about that.
All right. Well, we'll aim towards space-related questions. Will Suttles, who's on with us live, asks, why do galaxies often look like hurricanes?
Right. So it's an interesting analogy. I'd never heard that before. Hurricanes, yes. So they swirling morphology of some galaxies is of course the spiral kind, the kind that we live in, and they actually do have a range of shapes. We are in the Milky Way, so can't see it, but spiral galaxies do have a range of shapes, although they have spiral arms, and the arms, as you would imagine, trail the direction of rotation, and the rotation speeds are fast in absolute terms, but of course galaxies are huge, so at the distance of the sun takes 250 million years to orbit the Milky Way galaxy, 2/3 the way out. The spiral arms are essentially a pattern. They're not a constant situation where the features that highlight the spirals stay the same. The stars and gas clouds and dust clouds that form the spirals move in and out of the spiral arm in what's called a density wave. So they're not exactly like hurricanes. Hurricanes tend to be a little smoother and don't typically have spiral arms, well-formed spiral arms. In spiral galaxy morphology, there are so-called early and late types. The early types are smoother and have sort of more tightly wrapped arms, and the later types are more irregular, rugged, have blotchy H2 regions where stars are forming and dust lanes, and are less tightly wound and sort of end up almost being chaotic and not looking like a pure spiral. So these are the range of spiral morphologies, and they are caused by rotation, differential rotation in a flattened system where the inner parts are rotating faster than the outer parts, and density waves where the compression caused by the rotation make stars form in particular regions, and so we see those star-forming clumps as the bright outlines of the spiral pattern. Thanks. Ready for the next question.
All right, our next question is from Ruben P., who sent it in via email, who asks, how is it possible that we receive cosmic background noise from all directions if it supposedly comes from a single spot, the Big Bang? Is it due to the initial inflection point period of the universe, or the inflation period of the universe? I'm sorry.
Yeah, it's a good question. That doesn't have anything formally to do with inflation, so you can ignore the inflationary modification of the Big Bang. Just think about an expanding universe with a hot, dense early phase. Since in the expanding universe model, space-time itself is expanding, all parts of space are part of the expansion. So the expansion is happening everywhere. It's not happening in any particular space. So regions around the Milky Way, that space is expanding over time, and you could go billions of light years away and see exactly the same space-time expansion. So the signature of the Big Bang is not coming from a particular place. It's coming from everywhere because it was the entire universe that participated in this hot, dense early phase. And that means the radiation that's the signature of the Big Bang, the microwave background, originally very hot radiation that is now cooled and diluted by the expansion of space-time to microwaves, is also seen in every direction with almost perfectly equal intensity, not varying by more than about 1 part in 10 to the 5. So the Big Bang is not a particular place, it's every place, and the radiation that we see from it is suffuses through all space, including the space around us. And so there's no particular direction that's picked out in this situation. We see the same in every direction. Ready for the next question?
All right, thank you very much. So Richard Tennis, who is on with us live, asks, when the ESO Reach releases the first picture of the black hole on April 10th, what sort of image do you think we'll see? So this is a big news story that's been out from, we've been seeing a lot of press releases here at the University of Arizona, so we're excited about it too.
Yes, so the background here is that the press release will come not just from ESO, European Southern Observatory, but from the University of Arizona, for example, where we have one of the lead investigators in this project, which is the Event Horizon Telescope. So the project is a collaboration of radio astronomers worldwide. Many institutions are represented, including my own. And they're combining radio telescopes across the world to obtain extremely high resolution or sharp radio images of the center of our galaxy, the galactic center region in Sagittarius, where we know already from other work, independent work, that there's a 4 million solar mass black hole. And the reason radio telescopes are needed to do this work is the center of our galaxy is invisible to visible light. Optical photons just simply don't get here from the center of our galaxy. 26,000 light years away, there's too much gas and dust along the way. But radio photons come uninterrupted. They're not absorbed by that gas and dust. So if you want to see the center of our galaxy and the black hole that's there, you need to look with radio techniques. If you want to make a sharp image of the center of our galaxy, you need a radio interferometer. So a single radio dish will not be sharp enough in its imaging. You combine radio dishes with very long separations, which mimic the size of a much larger telescope, essentially a telescope the size of the Earth. And with that, you get the sharpest radio image that's ever been made of the center of our galaxy. And what they expect or hope to see, and they're pretty confident they have seen it, is not the black hole itself. The black hole is, of course, dark, but they will see the event horizon of the black hole, the point of no return for radiation and matter, silhouetted or backlit by hot gas swirling around the black hole. And that's the image they're going to see. And the shape of that silhouette, that sort of backlit event horizon, is very exciting because, first of all, no event horizon has ever been seen in astronomy. Black holes are known to exist by other evidence, but not by direct imaging. And second, the shape of that event horizon and the lit gas behind it will be a great test of general relativity because there are extreme distortions of space and time so close to a black hole, especially a big one, 4 million times the mass of the sun. So this is a very exciting event. They've been taking test images for a couple of years now, so they're pretty confident they have the capability to make an image, and they've obviously, put a lot of data together to get something spectacular for this first press release next week. Ready for the next question?
All right, thank you, Chris. That's fantastic. We are all, again, very excited about this. The next question comes from KN, who is one of our Japanese students, who emailed a question. And the question is, can we use supercomputers and astronomical simulations to predict the lifespan of planets or stars?
Definitely. Computers, they don't even have to be supercomputers now. Desktop, if you combine processors, a desktop system can be extremely powerful. Can essentially do now what a supercomputer 20 years ago would do. But powerful computers, yes, they're used extensively in astronomy and astrophysics now. They can be indeed used to predict the evolution of stars and their lifetimes, and especially how they will die. Actually, this evolution of stars is a fairly mature science. We've had a theory of stellar evolution for almost 100 years. And computers are not necessarily required to make models of how stars evolve, that those computations are quite modest. Where those kind of computers come in is in the spectacular end states of stars, particular supernova explosion. That does take a supercomputer to model it, and they've been very effective in doing that. So computers are powerful for modeling the end states of stars, or their unstable, spectacular ends. And in terms of planets, it's not so much the planets themselves, like the exoplanets we've been discovering, which are just assumed to be rocky bodies and similar to the Earth or similar to the planets in our solar system. Where the computers come in is in modeling the orbits, the long-term orbital properties of these planets. The solar system that we occupy and other solar systems tend to be stable for short periods of time, where that means tens or hundreds of millions of years, but over billions of years, they can be unstable. Planets can change their orientation, they can shift their positions due to interactions between them over long periods of time, and can be chaotic in a dynamical sense. And it really does take a powerful computer to model a solar system after following all the planets for essentially billions of orbits. And that does require very powerful computation. And that's been useful both for understanding our solar system, its past and its potential future, and for other solar systems. Ready for the next question?
All right, our next question comes from a live viewer, Shou Shin, who asks, could you explain the circumstances that cause tidal locking of moons to their planets? And does this also answer why there are exceptions in our solar system of moons that are not tidally locked?
Sure. Tidal locking is a gravitational phenomenon that occurs when a moon is particularly close to its planet and or a large moon relative to the size of the planet. Normally, for a moon that's far from a planet, it will have its own angular momentum and its own orbital characteristics. So the moon will be spinning with the angular momentum of the material from which it formed. Moons form around planets in a miniature version of the formation of a solar system, where the planets are orbiting the central star. And in a solar system, of course, the planets have their own spins as they orbit the star. But when the planet is very close to the star, or when the moon is very close to the planet, the force of the gravity on the front side relative to the back side of the planet or the moon is sufficient to sort of tug that moon into a front-facing position, where one face always faces the same way as it orbits the planet. Mercury does this for the sun, and our moon does this for the Earth, and other moons that are close to their planets will do this too. So it's a function of the distance and the mass of an orbiting object relative to the object that it orbits. And it's a standard phenomenon of gravity. So it's very predictable under what configuration tidal locking will occur. In the case of moons and planets, tidal locking, of course, changes the characteristics of those objects on their surfaces, because one side will be hot if it's a planet orbiting a star, and one side will be cold because it never actually changes its orientation relative to the star. And in the case of a moon, like our moon, means we can never see the far side of our moon without sending a satellite there because of the tidal locking. So it does have some interesting consequences. Ready for the next question?
Excellent. Thank you, Chris. Our next question is from another live viewer, Vatsal Lumba, who asks, in the course on Coursera, it has been mentioned that adaptive optics have given better results than the Hubble Space Telescope. So why are we all still mad about putting telescopes up in space?
That's right. So a few years ago, actually, it was another high-profile press release. We're talking about Event Horizon Telescope. Well, Steward did a press release a few years ago where the Magellan adaptive optics system on the 6.5 meter in Chile did produce a picture of a globular cluster that, scaled for aperture and light gathering time, was sharper than the Hubble Space Telescope image of that same globular cluster. So adaptive optics, the ability to cheat the atmosphere and take away the fluctuations caused by the turbulent atmosphere, has allowed telescopes to recover their diffraction-limited imaging. And then the imaging is better and better for a bigger mirror. We have much bigger mirrors on the ground than we do in space. And so if you can correct for the atmosphere, you can definitely make sharper images from the ground than in space. Then the question arises, why continue with space telescopes, especially because they're very expensive. I think per square meter of collecting area, telescopes in space are 10 to 20 times more expensive than telescopes on the ground. So you actually have to have a pretty good reason to do that. And the answer, there are several answers. The first answer is that for some wavelength regions, you can only work from space. Only a narrow sliver of optical radiation, factor of 2.5 in wavelength, reaches us from space. Shorter than about 130 angstroms, it's obscured by the atmosphere, and longer than a couple of microns in the infrared, the radiation absorbed by the water vapor in the atmosphere, with a few small windows to work in the near infrared. So for the ultraviolet, for far infrared wavelengths, and for millimeter wavelengths, and for everything to do with X-rays and gamma rays, you have to go into space. No other way to do the astronomy. So for those reasons, it is necessary to go to space. There's another reason, however, where the space environment still beats a ground-based environment, and that's the darkness of the night sky. Although you go to a dark site like Hawaii or Chile and the night sky seems very dark, far from civilization and city lights, there's a faint glow in the sky. It's called air glow, and it's caused by just the energetic OH ions in the atmosphere being excited just by ambient radiation or cosmic rays or ground heating, and it glows. So the sky is actually not completely dark. If you go into space, there is no atmosphere, there's no air, and it is utterly dark. So the sky is darker in space, and will always be darker in space than even the best place on Earth. And for some applications, and for very, very deep imaging, that does make a difference. So people are still motivated to go into space. Ready for the next question?
Excellent. So our next question is from email, from Evelyn T. Brook, who asks, I am doing a research project on the music of the spheres. I would like to bring my work to the present day, when I believe scientists are interpreting, she mentions planets, but interpreting planet sound waves as musical sounds. So do you have any resources that I could look at, or can you talk about any way that scientists use sound? And so I thought we could talk about sonification.
Sure. So sonification, the conversion of digital data into sound waves as opposed to an image, say, is a technique that's used quite extensively. It's not a major technique. It's not the way most data is represented, but it's a very interesting way to represent data. I think, for example, if you just Google NASA and sonification, you'll get a number of hits of very interesting projects that NASA has either facilitated or sponsored that use space data in various ways. So the harmony of the spheres, the original idea of Kepler, was based on converting the periods of the planet's motions, especially as perceived in their orbital speeds from the Earth's position, so offset from the center of the system where the sun is, into a series of tones. And so those tones would change as the Earth moves in its orbit and all the planets move in their orbits. Lower tones for the outer planets, faster tones for the inner planets. And you add them all together and you get a vaguely musical sound. That was Kepler's original idea from 400 years ago, and it's been realized since then a number of times. And there's sound clips you can get on the internet about that. Other sonification attempts have been done quite successfully, I think, with solar radiation, and one of those actually ended up being a performance piece that was at one point performed and touring on a tour with the Kronos Quartet using NASA data and NASA sponsorship. So that was quite a high-profile sonification of the sun's radiation. Cosmic rays have been done this way. Radio waves from galaxies have been done this way. So any sort of radiation that you can't see, invisible radiation, cosmic rays, radio waves, X-rays, it's a natural thing to do. Since you can't see this radiation anyway, you could convert it into a different form of sensory experience. Is really, really quite broad. Mark Whittle, who is an astronomer at the University of Virginia, I think was the first to do a sonification of the Big Bang radiation. He compressed the first 500,000 years or so of the universe after the Big Bang into a 4 or 5 second sound clip where he had to, of course, the frequencies are incredibly low because the universe is large, so he upscaled it by, I think, 46 octaves, and he compressed the time scale, of course, 500,000 years into 5 seconds. And you can also find that on the internet. And so people have done even the Big Bang with sonification. It's an interesting technique, has a lot of potential for making people able to experience something that they otherwise could not. Ready for the next question?
Excellent. Our next question is from a live viewer who asks, can someone study astronomy without attending university? So just with some math and physics tools, can one do observations at home?
Absolutely. There's an advantage to having some math and physics training, but there are many self-taught astronomers, and most amateur astronomers have not taken, they don't have an astronomy degree. Many amateur astronomers have a technical background. They may be retired scientists or engineers in other fields, but many are not. So it's definitely not a requirement to either appreciate or even study astronomy to have extensive math or physics background. I think at some level the math comes in useful and the physics comes in useful in understanding the phenomena you're observing. But amateur astronomy in particular is a very hands-on method where you're getting a small telescope with a CCD and taking images, and the images have their own visual impact regardless of the application of math or physics. So it's definitely possible to appreciate astronomy at a very high level without a lot of math or physics. Ready for the next question?
All right, our next question is from Sandra Gibson, who sent a question in over email. And she asks, what do we know about the galaxies that were recently identified as lacking dark matter?
So this comes up occasionally, that galaxies are ubiquitous in the presence of their dark matter, and on average in the universe there's 6 times more dark matter than visible matter or baryonic material, protons, neutrons, and electrons. That ratio tends to hold, but there are occasionally, in special circumstances, galaxies that either seem to be have less dark matter. It doesn't dominate the normal matter as much, or occasionally they don't seem to have much dark matter at all. And there have been a few recent claims of galaxies where there is essentially no dark matter. Usually what happens is, in that case, is we're talking about galaxies or systems where there's been a collision or an interaction, and the star component has been displaced from the dark matter component. And so when looking at the star component as it's been displaced by an interaction or collision, there's no corresponding dark matter. But it is there somewhere. It's somewhere in the vicinity, because the universe is suffused with dark matter. I mean, dark matter is found in the spaces between galaxies. So there's really nowhere in the universe we've seen where dark matter doesn't exist. But there can be situations, very particular situations, where there seems to be less dark matter than usual. And I think that's the one that's being alluded to in the question. We're ready for the next question.
Okay, our next question comes from Robert Sparkman, who is on with us live, who asks, is the up and down component of the sun's orbit around the galaxy having to do with the arms of our spiral galaxy, or does it have to do with something else?
So the motion of the sun around our galaxy in a roughly 240 million year orbit it's not a pure circular motion. It does have a vertical component. It's called the Z motion, since it's in the Z plane in that coordinate system that astronomers use for the galaxy. And so do all the stars around us, and so essentially do all the stars in the Milky Way disk. They have some vertical motion. None of them travel exactly perfectly in a plane. And the reason that they don't travel in a plane, and the sun included in that, is that the galaxy is not totally smooth, and the stars suffer interactions or gravitational attractions that tug them in a vertical direction, because there could be gas clouds or concentrations of stars that are slightly out of the plane, and those will tug a loose star or a nearly isolated star like the sun towards them, or up or down. And it's an oscillation like a pendulum, because eventually, if the sun or any star oscillates much above the plane of the Milky Way, the plane of the Milky Way as a whole will pull it back down, and then through, and then back up on the other side. Since stars don't collide, this oscillation is a sort of sinusoidal motion. So the true motion of the sun and other stars around the galaxy is a sort of sinusoidal up and down motion, the z motion, along with its much larger circular motion. And this is a phenomenon shared by all stars. Astronomers use the z motion, the vertical motion of stars in a galaxy like ours, to essentially weigh the disk of the galaxy, because those vertical motions that move in and out of the plane and the restoring force that pulls them back into the plane is a measure of the mass of the disk. Ready for the next question?
All right, the next question comes from Vandanap Singh from email, and they ask, as our sun is a main sequence star converting hydrogen to helium, where does it get its magnetic field from?
So the sun's magnetic field and the magnetic field of all stars, because essentially all stars that we've been able to inspect carefully enough do have magnetic fields. The magnetic field is primordial, which means the magnetic field was pre-existing before the gas cloud that formed the sun collapsed. So basically, there's a whole theory of astrophysics that leads to the understanding of where magnetic fields in astronomy come from, especially in galaxies and on large scales. There's a dynamo mechanism whereby charged particles, because these gas clouds are hot, so the particles are not neutral. They're not neutral atoms. They're hot enough so the electrons and the protons are separated. Turbulent motion in a system of charged particles can lead to the creation, the generation of magnetic fields. It's called a dynamo effect. And so a region where a star might form, a very diffuse gas cloud that will collapse by gravity into a star, is already threaded by a very weak magnetic field, this primordial magnetic field caused by this dynamo effect. As the star collapses under gravity, the magnetic field lines are essentially trapped or squeezed in the gas as it collapses, and so they get closer together, more concentrated, and so the magnetic field rises. So by the time a diffuse and very nebulous gas cloud has collapsed into a star, the very small primordial magnetic field has been amplified into something quite strong. And then in the plasma of the sun, plasma being the charged particles moving independent of each other, that magnetic field is now trapped in the plasma. And so the magnetic field of the sun is threaded and then squeezed as the sun collapsed. It emerges from the poles into a dipole, just analogous to a bar magnet. And that's what we see in the sun and all the stars we've investigated so far. The magnetic field of stars can vary quite substantially because their internal structures and their sizes and masses vary quite substantially. But that's a ubiquitous mechanism in stars. Ready for the next question?
All right, the next question is actually several people have had a similar question, but I'm going to read the one from Surya Shivaprasad, but Will Suttles also has a question related to this, and it's about thermodynamics and sort of the acceleration, the expansion of the universe. So in the heat death scenario, the accelerating expansion of the universe causes everything to get stretched apart and all the stars eventually burn out and black holes fizz out via Hawking radiation. So eventually the universe cools down completely and tends to absolute zero. But since everything cools down and inches closer and closer to absolute zero, doesn't that mean that the entropy of the universe is tending to a minimum? Doesn't that throw the second law of thermodynamics into the bin? And Will Suttles asks, what cools down or what warms up as the universe cools down? So these are related.
Right. So the terminology is a little confusing because astronomers, cosmologists talk about the heat death of the universe in its endless expansion. And as the questioners point out, in the expanding universe, when eventually all the stars go out and the space between stars gets bigger and bigger, and so radiation is diluted and lowered in wavelength or energy, making longer wavelengths and lower energy, that's actually a cold situation. The photons, the radiation is extremely cold. So in terms of the radiation, the universe as it gets bigger is a cold universe. In the heat death of the universe is really alluding to the fact that the entropy is still increasing, which is to say that the disorder is increasing. And heat, for example, unordered, disordered radiation with no structure is a high entropy state because it has maximal disorder. There's no structure. So it's in the sense of loss of structure that the universe is going towards a heat death or a high entropy situation. And so if you track the entropy of the universe, the entropy is not decreasing, it is actually increasing. So the law of thermodynamics is obeyed in this situation. And the reason the entropy is increasing is because the structure is gradually being lost. There's a process in the long history of the future of the universe where galaxies slowly evaporate, where stars are lost. They're not gravitationally bound, but they fizz off in intergalactic space, where the same thing happens within solar systems and planets are lost from their parent star. And so in a very, very direct sense, the structure of solar systems and star systems is gradually lost over time. The universe tends to a more uniform state, independent of the radiation itself, which is also diluting and cooling. So the future universe is a very disordered system, and it has very high entropy, and that entropy continues to grow. Black holes are a slight exception to this because black holes, of course, are structures. They're sealed off parts of space-time, but even they will eventually participate in this heat death because of Hawking radiation. So on the very longest timescales, black holes evaporate and so turn into radiation. Their structure is lost. Their identification as a collapsed object is lost eventually, and that is what reflects the final heat death of the universe on an exceptionally long time scale. Ready for the next question?
All right, our next question comes from a live viewer. Amila Basnayaka asks, how many extrasolar planets have been found, and what type of methods have been used to find these planets?
So the body count of exoplanets is of confirmed exoplanets is over 3,000, 3,200 perhaps. The number of candidate exoplanets is over 4,000. And most of the candidates that haven't been confirmed will turn out to be correct because the methods are quite sturdy and success rates are 90% or higher. So several thousand, most of them in the last 5 or 6 years. And most of those successes in the last 5 or 6 years have been found by the transit or eclipse method, initially, and particularly by the Kepler satellite, which is no longer functioning in its normal and productive mode. But for 5 or 6 years, it was producing huge amounts of data in one region of the sky and finding hundreds and hundreds of exoplanets, press release almost every few months. So the transit or eclipse method using the Kepler satellite has been the single most successful means of finding the majority of all the exoplanets we know of. The Doppler method is still used, and I'd say the Doppler method was certainly used to find the first few hundred exoplanets before transits kicked in, and it's still used to find exoplanets. So perhaps 500 or 600 now have been found using the Doppler method, which gives you the mass of the planet but not the size. Transits give you the size but not the mass. And a few hundred have had both methods applied to them. And so we know more about them because we know how big they are and how massive they are. And so we have a sense of their mean density, very valuable information. And that's sort of the gold standard for exoplanets, is to have both of the two primary methods in play so that we can learn two fundamental things about each exoplanet and get a sense of whether, for example, they're a rocky planet, a terrestrial planet like the Earth, or a gas giant like Neptune, Uranus, Jupiter, or Saturn. Ready for the next question?
All right, the next question is from Stavros, who sent a question in via email. Is there an explanation for why most of the hot giant planets that we have found so far outside our solar system are so close to their stars? And why doesn't this happen in our solar system?
So the phenomenon of hot Jupiters, which is what the question is alluding to, was initially a surprise. The first exoplanets to be found, 51 Peg was the archetype, found in 1995. It's a half Jupiter mass planet on a 4-day orbit of its sun-like star, so incredibly close. Think about that, 4-day orbit, dozens of times faster around its star and closer to its star than Mercury is to the sun, and it's a huge planet. No such planet exists in our solar system. And many of the first discoveries were these hot Jupiters, not all of them, but many. As people have gradually done more extensive work and bigger surveys, we're starting to fill in the picture of exoplanets. And now we do not think that hot Jupiters are the majority of the large planets out there in the universe. What happens is you find the easiest things to find first when your techniques are limited by sensitivity. And a massive planet close in pulls its parent star more strongly than a massive planet further out. So it's easier to find by the Doppler method. It also produces a higher probability of an eclipse and a bigger eclipse. And both of those things lead them to be found by the transit or eclipse method more easily than a giant planet further out. So for all the detection methods, the subset of planets that are hot Jupiters or hot Uranuses or Neptunes are the things you're going to find first. So you find them very efficiently, and you find all of them, all the ones that are out there. If you want to find Jupiter, a Jupiter like in our solar system, well, first of all, its orbital period is 12 years. So by a transit or a Doppler method, you need at least 2 orbits to be sure you've seen that planet. That's 24 years. Well, we've barely been studying exoplanets for 25 years. So only now have we got enough data to find giant planets in their normal giant planet positions as in our solar system. And as we have that much data, we're starting to find them. So it's a little too early to tell what the true distribution of exoplanets is, but the prevalence or the early prevalence of hot Jupiters was a little bit of an artifact of the sensitivity issue. Now, the fact that they exist at all is still interesting, because we know that a hot Jupiter could not have formed at the position where it's seen. There was not enough gas early in the history of a star and its formation to form a massive planet there. So it's been known for a long time from theoretical grounds that these hot Jupiters and Uranuses and Neptunes close into their stars must have moved there. They formed further out and migrated inwards. So planetary migration was a very quick and important implication of the detection of hot Jupiters. And we now understand that planets in their solar systems move around quite a lot, and it's not an unusual phenomenon at all. Ready for the next question?
All right, our next question comes from Craig, who's on with us live. I've been curious as to how stars are able to move apart from nebula. I know stars are created in nebula, but how do they eventually get out?
That's a good question, and it happens for a couple of reasons. So the stars form from a large gas cloud, which may have some rotation. It collapses by gravity, and if all this material, the stars and the gas, the nebula is basically gas and dust. So if all the material, the stars and the gas and the dust that formed them was in the same region of space held by gravity, it doesn't seem like they should ever separate. So intuitively, it's a really good question, because why should the stars ever leave the system? They all formed from the same large gravitational system. The 2 reasons that you can find stars separated from their nebulae, or the nebulae that formed them or surrounded them when they were born, are that when the stars form in a dense star cluster at the center of a nebula, which is a typical situation. You look at the Orion Nebula, you're seeing that happening. You're seeing a dense, tight star cluster at the center of a larger nebula. When those stars interact as they form, they create, they interact very strongly by gravity, because they're moving fast and close to each other. And their interactions can lead to slingshot mechanism, where some fraction of them, obviously not all of them, but a fraction of them are ejected from the system. So the transfer of energy and angular momentum between stars as they interact in a dense star cluster leads to the ejection of some of those from the system. So it's a completely natural gravitational phenomenon that stars will be ejected from the region they're born, and then will be seen flying through space at quite large velocities away from the nebula where they formed. The other reason is that the stars themselves, of course, interact with each other by gravity, but they don't collide. So they tend to stay in the same place. But as the big unit that has formed by gravity, the stars and the dust and the gas all together move around the Milky Way through our stellar system, the gas is viscous. The dust and the gas, when they meet other regions of dust and the gas, they will collide and stick together or collapse or form shock waves, whereas the stars will pass through unimpeded. So in interactions between a nebula and a surrounding region of denser material, the stars will not interact in the same way. They will essentially not see the other material. They will continue to move in the same direction. And so a nebula can become separated from the stars that it formed for that reason too. So it's not that unusual to see it. The third thing that can happen is the nebula can actually dissipate over time. So the gas can just gradually dissipate into interstellar medium, be less concentrated. The heat from the stars, the young stars that form, can ablate the gas or drive it away, and so dissipate the nebula that formed those stars. So these are all reasons why you can have a situation where the stars and the gas and the dust or the nebula are not in the same place. Ready for the next question?
All right, thank you, Chris. The next question is from someone who obviously wants to remain anonymous, YYY8888, who's on with us live, who asks, is there a universal unit for measuring distance? For example, what would we do if we meet some intelligent aliens and we want to communicate distance? Our measurements of kilometers and light years are Earth-centric.
That's right. So we do have an issue if we want to communicate physical quantities to alien intelligences, for example, or just have a consistent way of doing it. It's true, our systems of units are a little Earth-centric, a little human-centric. The metric system, for example, is a little arbitrary. I mean, it's a lot more sensible than the English units that preceded them, which were not based on decimal quantities. So I think the fundamental measurements of length, and in fact the meter used to be, as most people probably know, used to be a standard highly pure metal rod kept under vacuum in the National Institute of Standards in Paris, France, home of the metric system. So there was a meter that you could refer to. But people, astronomers and scientists, realized that that meter actually changed length according to temperature, and little atoms would fall off of it, so it would be changing its length slightly. So meter is now determined, or it's quantified or defined in terms of wavelengths of light. So that's probably a more fundamental way to talk about distance or length, is to use wavelengths. The question is, what wavelength would you use as a reference point? Because light comes in all different colors, all different wavelengths. And so where do you set your limit, or where do you set your wavelength? One way to do that would be in terms of atomic properties. So there's a wavelength of light, for example, that's in the ultraviolet, and it corresponds to the ionization potential of a hydrogen atom. So it's the wavelength of a photon that will liberate an electron from a neutral hydrogen atom. That's a very logical wavelength to define in nature that would be meaningful to anyone elsewhere in the universe of whatever function or form, because it's based on fundamental atom of the universe, hydrogen, and its atomic properties. So that's probably the most logical way we define wavelength if we wanted to communicate with other species, other intelligent aliens. Ready for the next question?
All right, we have a next question from one of our live viewers who asks, is there any essential difference between the sun and G stars located closer to the center of our galaxy in terms of chemical composition?
Yes, the galaxy and all spiral galaxies like ours have what's called a chemical gradient. So the density of stars is higher near the center of our galaxy than in the outskirts. We're sort of near the periphery, 2/3 of the way out. And so there's a gradient where there's higher abundance of heavy elements, or metals, as astronomers call them, towards the center of a galaxy, a spiral galaxy like ours, than towards the periphery. And that's, of course, because the star densities are higher, because massive stars are cycling through their elements and ejecting gas into space that forms a next generation of stars. So stars are more efficiently cycling through their lives and then forming with the residue of previous generations of stars, and so more of the heavy elements they created. So the heavy element fraction of all heavy elements more than hydrogen and helium increases continuously and smoothly as you go towards the center of the galaxy. And we can see this in the spectra of stars. So we can look at stars that are just like our sun. They have the same mass, the same surface temperature as the sun, and on average, those sun-like stars in the center of our galaxy will have a larger fraction of heavy elements than the sun. Not by a dramatic amount, maybe 30 or 50%, perhaps a factor of 2, but it's a very systematic and clear effect. Ready for the next question?
All right, thank you, Chris. Our next question is from a live viewer who asks, what is the newest explanation for the matter-antimatter asymmetry? Have we had to rethink the energy-matter conservation law?
The best current thinking, this is an active area of research, why the universe is composed essentially of matter and not antimatter. And the related information is that there are about a few 100 million or about 1 billion photons for every particle in the universe, and essentially no antiparticles. Those two things are presumed to be connected. It's not a violation necessarily of it is a violation of the conservation of energy and the conservation of what's called baryon number, where the number of particles and antiparticles in interaction is supposed to stay the same. And it's presumed to be caused by what we'd say were initial conditions early in the universe. So at the time, the radiation that we see all around us, that's now the residue of the Big Bang, billions of years later, was formed. There was a time when the universe was symmetric. It was matter, antimatter, symmetric, almost equal numbers of particles and antiparticles. But in the grand unified theories that talk about the merger of all the three forces except gravity, there are mechanisms whereby there can be a very slight asymmetry between matter and antimatter. And when eventually the matter and antimatter annihilate, lead to an abundance of photons and very few normal particles, that slight asymmetry turns us into a universe full of radiation and a tiny amount of matter and essentially no antimatter. So this mechanism arises from the grand unified theories, which are as yet untested and they're speculative at some level. So I don't think we can fully understand why there's no antimatter in our universe. Ready for the next question?
All right, Chris. So this is going to be our final question of the day. This is from Eric Nicholson, who asks, did I understand that at the beginning of the Big Bang expansion, it was faster than the universe expanded faster than the speed of light? And are there events now which are faster than the speed of light?
Yes, the expansion, the separation of any 2 points in space early in the universe was faster than light. The universe expanded, and the physics term for that is superluminal, faster than light. And any 2 points in space were moving apart faster than the speed of light for all the first third of the history of the universe, the first 4 or 5 billion years after the Big Bang. The universe in that period of time was decelerating because of dark matter. Dark energy had not yet come to dominate the dynamics of the universe. That happened in the most recent 5 billion years. And so the superluminal expansion of the universe is a function of the extremely fast early expansion, where pieces of space-time are moving apart faster than the speed of light. That those regions of space that really couldn't be seen by each other because nothing travels faster than light would come into view of each other as the universe decelerated. And this is called the horizon. So regions of distant space-time that were outside of our horizon because of that early, very fast expansion have come within our view again over cosmic time. There are galaxies that we couldn't have seen early in the history of the universe that we now can see. The future, of course, plays out in a very interesting way because the accelerating expansion of the universe means that any 2 points in space-time are now going to start moving apart faster and faster, and at some point they'll become superluminal again, as they were in the early part of the universe's history. So it's certainly possible that there are very distant galaxies which once upon a time we couldn't see because they were moving away from us faster than light, which subsequently we were able to see, or maybe are able to see now, which will once again be wrested or ripped from our view as the accelerating expansion continues. A very bizarre situation indeed. Okay, that was a nice set of questions. Thanks very much for all of that. And thanks to Matthew and Vicky and Alexander for facilitating this session. And as I think you know, and you'll see elsewhere, we're right on the cusp of launching our astrobiology MOOC, and very excited about that with Coursera. And we'll be continuing our live sessions, I think, in 2 weeks. We'll try and keep a cadence of every 2 or 3 weeks. So we'll see you in a few weeks. Okay, bye.
Excellent, and thank you all for joining us today. We the astrobiology course should be launching on Monday, so please look for that in Coursera and check it out. So we hope that you have a fantastic weekend. Bye-bye.